not useful for porting the kernel to a new device. So if I want to make Linux work on something new and interesting, I actually want to go to kernel.org and download the source code from there. I do not want to use the Fedora kernel sources to build a kernel for this. Okay, that's not what it's been geared, designed for. Having said that, if you are doing development, you are working on Linux for interesting gadgets and devices, then some of the vendors in that space who will sell you embedded Linux products, they intend for you to take their kernel sources, their special modified version, and to use that instead of the kernel.org source. Sometimes they'll do this if they've added their own features, their own drivers, their own additional options that they want you to use. But generally, you want to use kernel.org as much as you can. Okay. So, I'm not going to go through all of this because it would take hours, but configuring the Linux kernel, after you've downloaded the kernel source, you want to use this command, menu config, make menu config, to configure up the kernel. You want to choose which options you want to build in, which kinds of disks you want to support, which kinds of USB devices you want to support, what kind of file system. Do you want to support your ext3 file system that's on your hard disk now? Do you want to support the Andrew file system because you've got a server, a few thousand miles that way, and you'd really like to use its storage as well? You can configure different options. Most of the time, your vendor will have configured your system with pretty much everything built as a module. So anything that can be built in a modular way, that is to say it can be loaded later, it can be added to the system at a later time, they will have built it that way if possible. After you've configured it, you run make, and you wait a while. A lot less time these days. I still remember the days when you were looking at 6, 7, 8 hour compile times. Now you've got to wait 20, 30 minutes maybe. You compile a lot of things in there. You go make a coffee, come back. Standard kind of thing. Okay. After you've built it, you can install the kernel. You need to install it, you need to make it available, you need to set it up so that when you start your system it's going to be used. So the first thing you do is you install the modules that your kernel provides, anything that can be added to it later. They live in a standard location, so you want to install those using the make modules install command. You want to install the kernel itself according to whatever instructions your Linux vendor provides. Again, it does vary from one system to another. Broadly speaking, they live in /boot. And broadly speaking, there'll be some kind of command or utility that your distribution provides to wrap this all up for you. So you can, in the case of Red Hat, you can run a new kernel package, and its job is to kind of handle a few of these things for you. So you will have to follow your distribution guide. The exact process will vary. Okay, so that's how you build a kernel. That's how you configure it. That's how you build it. That's how you can reboot your machine and fundamentally be at the same point you were at 10 minutes ago. So what was the point in building all that stuff? Why did we bother? I mean, we're still at the same point we were at. Well, not really, because we're not going to be able to write any drivers for our system. We're not going to be able to extend our system unless we have built the kernel sources. So we've now done that. We're now at a point where if we want to write new drivers, new modules for our system, we can do that. We can take the source we just built, we can use that as a reference to build modules for it. So we can add new drivers, new kinds of hardware. If I get a new PCI card for a new sound device, something like that, I can build a driver for it. I can add a new file system. If I want to use my Gmail account as a file system, someone has written a driver to do that, and there are different ways of doing that as well. You can use Fuse, or you can use kernel modules, all kinds of different things. You can't change the core kernel. You can't change something that's fundamentally in the kernel through a driver or a module. So for example, if I wanted to change fundamentally how Linux views memory at a very basic level, I can't do that in a module. That's not what it's designed to do. Modules are designed to take the interfaces and features that are already provided by my kernel and add one specific new thing, one new kind of device, one new kind of file system. They're not designed to go and change everything underneath it. So sometimes you have to modify the kernel itself. We'll talk about that in a minute. So here's a sample module. It's nothing too fancy. If you want to get more into modules, you're going to get a hold of one of the books and read it. It'll go through how to actually write modules for different kinds of device. But this module here simply prints hello world to the kernel ring buffer, the kernel log, and go ahead and view the output by checking in your system logs. So you can compile up this function. When it's loaded, it's going to print the message hello world into our system logs. I'll show you how to get that out in a minute. The point is, here's an example. It's not too long. About a page and a half of text, including some documentation here, module author, description of what the module does, and the license, very important there. These are standard macros here that you always include that provide sort of information about the module. The license is important. If you don't provide a license, then when you load that module later, the system is going to think it's been tainted. It's going to think that you've added a module that's not GPL, that's potentially proprietary. That means that your system, your kernel itself, is no longer purely GPL. That's where these taint messages come from that you may have seen in your system logs before. So you need to have a license in there. Okay? I'll just kind of cover a couple of points in this. Yeah, Chris?
John, where's the hello world function being called from?
Sorry, yes. It's a very valid point, thank you. I need to remember to change my slide back again. Okay, so...
He exports the symbol.
Yeah, I export the symbol hello world, okay, but I don't actually call it. Chris is right. When you load this module, you get loaded module printed into your log. You get unloaded module printed when you remove this module from the system. The actual call at hello world, I did actually take out. But if you put in a call here to hello world, then you could call it. The other point being, I have this macro call here, export symbol GPL. Thank you, Chip, for pointing that out as well. I'm exporting this symbol, so it means that I'm making that hello world function available to other modules in my system as well. If I want to build up a set of modules that use different functions from each other, then I have to say, I want to make this function available to other kernel modules. So I have to have a line like this, export symbol, in order to make that function available. So no, I don't call it here, but if I call it somewhere else, now when I go ahead and build up some other module, it can figure out, okay, I need to have this hello module loaded first in order to make that function available. Okay. Now, so we cover a couple of other points here. So, if you ignore the left-hand side here of this example, and you just concentrate on the right-hand side, you'll see at the top we have the metadata about this module. Okay, we have defined entry points. We have a macro here called module init that says when this module is loaded, call that function. So whenever I do a mod probe or an int mod and load this module on my system, it's going to call this function here, hello init, that's been specified. Whenever I remove the module, whatever's in here, module exit, is going to get called, and that's going to result in a call to hello exit, which will result in unloaded module being logged into the system log. It doesn't go to the screen. Where would we put it? We don't have like a kind of fundamental concept of a screen to which all kernel messages will always go, where the user's always going to see them. There might not be a screen on my machine. So they'll go to the console, but we won't get into that too much. They're not necessarily going to be visible by the user, sitting in front of a machine somewhere. They're going to go into a log. That's what printk does. It prints the message and puts it in a log, which we can then view. I'll show you how to do that. So first I'm going to take the source code I just wrote for the simple module. I'm going to build it. In order to build it, I need to have this kbuild file. I need to tell my Linux kernel build system how to build this module. Okay, so I put in a couple of entries in a file here. I say, okay, I'm going to add a new module. I'm going to call it hello module. And by the way, hello module requires hello to be built first. So simple make rules, okay, for those that have written make files before. And then when I make a call to the make command from within my existing kernel source, I can build this module for the kernel that I built before. So I write a simple file here, I call the make command, and at the end, out comes a module that's been built against my kernel. Again, you can download these slides. You know, there's no point kind of going through every single line. I'm trying to make the general point here. If you want to go through the example line by line, then please download the slides later. You know, go through them, and you know, it'll make sense, I hope. If it doesn't, you can email me, and I'll try to explain it. Okay. You need to install that module. You need to make it available. Otherwise, your system's not going to know how to load it. I can sit there, I can type mod probe until I'm blue in the face, but you know, unless I've actually put that module somewhere, I'm not going to be able to use it. So I make a call to modules install. It puts that module into the lib modules location where all my standard system modules are located. Okay. Having done that, I can then use my mod probe command, mod probe hello, and I can check in my system logs. I can see it's reported that it loaded the module successfully. I can also remove the module, again using the mod probe command, and I can see in my logs the module has been removed.
There's turning the lights down just a little bit.
Okay.
I'm trying to.
Okay, so before I get on to the next section, are there any questions about, I know that was very quick, it's just I'm aware that we've only got a limited period of time to cover a lot of stuff here. Are there any questions about configuring a kernel and building up the example? No questions from those? Yes?
So you exported a symbol,
Yeah.
and I was wondering if I can still call that symbol when the module isn't loaded yet.
So yeah, when
yeah.
you okay.
So would it mod code for me if I call hello
Yeah,
world from another?
So when you've built the module using the make command there, you make this called a detmod. And detmod generates a bunch of files under lib modules. Not only are your kernel modules themselves located there, but also a file called modules.det. There's a PCI aliases file in there as well. So if you've ever wondered, how does your system, you know, when I plug in a new sound card, how does my system know that it's got to load that driver? I mean, it's not magic, right? What we can do is we can actually provide that kind of information through macros as well in our module. So that when we run this detmod command, and most distributions will either call detmod when they boot up, or they'll have some kind of process for automating rerunning detmod for you as well. But when this runs, I also produce other files that contain information about, here are the drivers that support this PCI device, or here's the driver that supports this other device. Here's the dependency information. So the dependency information is also generated at this time. If I have another driver I'm going to load, and it has a dependency on my driver, that's how it gets resolved. The other driver's been built, this command has been run, it's all worked out. Okay, if he tries to load that module later, I'm going to have to load this one first. Okay, so that's how, if we provide a new symbol, that's how, you know, if someone wants to come and use this, during the build process, it's going to work out, okay, there's an unresolved symbol. What do they need? They need hello world. Okay, what other module provides that symbol? Okay, there it is. I'll put that into the dependency tree. So when the other module gets loaded, this one gets pulled in automatically. That's how automatic module loading actually works. It's not magic. It just relies on non-circular dependencies. So for example, I can't have two modules mutually depending on each other in sort of complex circular fashions. That's not